Hello, everyone. Uh, how was the contest, guys? Any comments on the contest? Can you guys hear me? All right, say something in chat if you can hear me, cause not very sure. No one's saying anything. Something. Okay, perfect, perfect, perfect. Okay. Um, I think I'll just well, I'll just go ahead. Let's go. Let's start. All right. So, so today we're going to be going over two of the problems that you guys voted for. If you didn't see, I posted a poll on Discord with all of the ACPC problems. Um, and you guys voted for hired help as one, and the other was password rotation. So they're both fairly difficult, based off of like the solve percentage and the average percentage. It was pretty difficult, and that's why we're gonna go over them. So I'll start off with are we doing Minesweeper? No, we won't be doing Minesweeper today. I know that I believe next week we'll be going over Dante's problems. So Dante actually wanted to teach his own problems, which includes best investing is one of his problems. You guys can check by checking the author. Dante's here. I don't remember what other problem he did though, but I don't believe we'll be doing Minesweeper. Yeah, okay, Noah did that one. If you guys do want to learn how to do Minesweeper though, I could try and prepare it, or I could try and get like one of the setters to who actually created it to try and like walk it through with you guys. But so today I'll be going through hired help and what was the other one? Password rotation. Okay, so we'll go through hired help first. So I've highlighted most of the stuff that you actually need to know for the problem. If this is like the first time you're seeing this problem, then it might be a little intimidating at first. So basically, we're given a value named k. This k value is uh, the maximum amount of shoes that a employee can basically clean, I guess, or repair every single day. And it takes 1 minute for it to repair. Each shoe has its deadline. So we're basically going to be given a deadline for each shoe over here. And that's part of it. Case shoes, today one Viv would prefer to not have them hired at all. So basically what this means is that every employee has to do K number of shoes. So if it's like 3 shoes, then everyone can't do more or less than K. They have to do K. If they do less, they get fired. If they do more, it's bad for Viv. So Viv doesn't want that to happen. In fact, she believes in this so strongly that she would prefer to lose business from clients than to have an employee not complete their quota. So what that means is like about the same thing that we have with this K variable. Help Viv determine the maximum number of employees she can hire. So A, each employee can repair K shoes before their deadline, and B, each shoe is of course repaired by at most one employee. That makes a lot of sense. So if we look at the inputs, we're given two integers, n and k, where n is the number of shoes that need to be repaired, and k is basically the threshold, the quota. So the maximum and minimum, I guess. Then in the second line, wait, we don't need to read that. That's okay. In the second line, it basically just talks about each shoe and what these numbers actually mean. So this would be minute 2, minute 1 of the day. As you can see over here already in the input, they're not in order. So that's something we have to take into consideration when we're creating the solution. Now with the output. So output a single integer m, which is the maximum number of employees. So let's run through some of these sample inputs. So 6, that makes sense because there's 6 inputs here, and 3 is our threshold. So every employee has to do 3 shoes within the full entire day. And we know that since it takes 1 minute per shoe, that means that an employee can't do like 2 shoes in 1 minute. So an employee can't do like 1 and 1 to make, and then like 1, 1, and 2. You can't do that. They have to be like in order or in separate times. So in this case, once we've sorted the actual array, we would get 1, 1, 1, 2, 2, 2. And since none of the employees can do 3 shoes, then they won't. The output will be 0 because none of them will be hired. A similar scenario goes over here. So once we've sorted this out, we actually have 2 employees that are able to do 3 shoes within a day. So that'd basically just be like one employee doing 1, 2, and 3, and then the other employee doing at minute 1, 2, and 3 again. With this last input, things get a little interesting on basically the idea that we need to have when creating this algorithm. The reason I say that is because once we've sorted this array out, we'll get 1, 1, and then 3 2s, and then 1, 3. Basically, what that means is that since we have 3 2s over here, one of these has to be like cut out for sure. If we're going from the beginning of the array, this sorted array, we know that the number of ones that we have, the number of shoes that have a deadline of 1 are 2, right? So that means that if we are looking at hour 2, or I guess minute 2, since the frequency is higher, and when I say frequency, I mean like the number of shoes that we have in this situation is higher, it wouldn't really work with RK. Um, it's a little confusing right now, but like I'll it'll make more sense when we actually visit the program that we're the solution, I guess. All right. Here is the solution for hired help. So, this isn't my code. This is the actual problem setter's code, Zach. He made this, but I'll be like annotating it and like telling you guys what's correct about it and like how it works. All right. So, this stuff is fairly straightforward. Right here, we're just like, importing n and k. Then, as I said before, we want to sort the array from like lowest to highest in terms of time, I guess. So once we've sorted the vector out, then we're good to go. Next, we want to create 2 variables, one named low and one named high. So what we're trying to achieve in this algorithm is basically have a boundary at what's the maximum number of employees that we could possibly have and the minimum number of employees that we could possibly have. So the minimum is always going to be 0 at the start of our algorithm. And because of how the problem is phrased, our high is always going to be n plus 1. Because, because when you like think about it, like let's say we have like an array of like ones and our k is like 1 or something, then the maximum and the lowest value of k is 1, which would result in the maximum number of employees, right? So that means that our maximum number of employees has to be equal to the length of this array, which is n. Alright, then we go into this while loop. This while loop is basically a comparison between the two. And what we're trying to achieve here is we're trying to decrease the range at which the number of employees that we have is like correct. So we know that the number of employees that we have is like the correct amount when either the low is greater than the high or the high is lower than the low. So the first variable that I create here is called m. M again is like the maximum number of, well, like from like our output basically. And what we do over here is we want to find the sum of low and high, and this right here basically just moves the binary version of low and high. Uh, it removes the last digit of the binary version, so it essentially just divides the sum of this by 2 and rounds it down. So I'll give you guys an example. So say low is equal to 0 and high is equal to 3. Alright, so when we add the two, so low plus high is equal to 3 obviously, and the binary version of that would be, I'll give it in 4-bit binary, but it'd be equal to this. Now, what this program is asking us to do is remove the most recent one over here. So if we remove it, that means that we get this. So this in decimal would be equal to 1. So what it does is it just divides it by 2 and rounds it down. So you get 1.5 and then we round it down, so it's equal to 1. So that's literally what it does. Think of m right now as like a sort of a guess. It's similar to how binary trees work, in which, or like quicksort, where like we're looking at the array that we've sorted, we're choosing like a middle value, so then we can like cut our like estimation by half every time. So either there's two cases when we do this. Either m is too small or m is too big. In each case, we basically cut our range down by a half. Alright, so now we have a new variable called tote. Basically, what tote does is that it's like our counter for now. We're gonna use a for loop to go through the different number of to go through our vector, and we're basically gonna compare the two. This might seem a little confusing at first, but I'll go through it. So x times m is like a cap. Basically, it's our estimated cap of the number of like possible. It, okay. For every time slot, a maximum of m employees can be working on is basically what it is. So therefore, only false if frequency is of x is less than m. Sorry. So what that means is that when we have like a new vector over here, right? Let's say we basically guess like m is always going to be half of our vector, and we want to make sure we want to basically add tote every single time we see like a possible job that we can add. It's a little confusing right now, but I'll try and it'll make a little more sense when we go on. So tote, just think of tote as like the possible number of shoes that we can like work on at a time. And since this is like half our value, we know that if tote is greater than, if tote is like greater than this value, then we know that the low has to be moved up, I guess. Sorry, it's a little hard to explain. Basically, in this if statement, we're going to compare tote to m times k. M times k is the full maximum, well, the maximum number of shoes to clean. Thus, if tote is greater than or equal to m times k, then our guess is too small. And if our guess is too small, then that means that we can move our lower boundary up to m. And then if tote is smaller than m times k, then that means that too many predicted shoes were actually there, so we have to actually bring down the upper limit of our range. So essentially what this program does is that it cuts down the range in which the number of employees that we can have is possible until we get to the exact amount. This function over here, let me try and re-clarify a little better. This function over here basically checks to see the number of possible shoes that we have in a specific time slot. So for example, this thing would only be false if we have more than uh, m shoes at a specific time. So for example, if we have our m in this case would be equal to 2, right? Because we're trying to find, we divide it by 2 and then blah, blah, blah. So it's equal to 2. What this means is that when we compare the two, our tote will only go up until 2. Because once we multiply this x value, which is this, by the m, it only hits 2 and then it stops right there. Does that make sense a little, guys? Make sense? It's literally just like a cap on the maximum number of shoes that we can have at like a specific time. But it's like an estimated cap. So we're trying to estimate the number of employees that we have, which means that we have to have this like cap there. Yeah. So this program will keep on looping until we've actually hit the number, and we know that we've hit it is when this low and the high intercept, therefore it will jump out of the loop. So this is definitely one of the more efficient ways of doing it. And then we just print low at the end. Alright, I hope that made sense for some of you guys. I will be moving on to password rotation. So password rotation is a fairly straightforward problem. It's difficult to implement, but the actual ideas around it and the actual problem itself, like what it's asking for, is fairly straightforward. Basically, what this is saying is that we're given a password, and a password can be rotated in these number of ways. So these are all the possible rotations for A, B, C, D. So the A moves to the forward, moves to the end, and the B becomes like the next value there. Yeah. So we can also do reverse rotations too, which is something that we have to note. Basically, this n is the number of passwords that we have, and we're just trying to figure out if one of the passwords there are a rotation or a reverse rotation of all of the other ones, of one of the others. So once we've seen one rotation, it doesn't matter if there's like 2 rotations in here. Once we've seen one, we just output yes, and then we're done. We're done with the program. The only time where we output no is if we can't find the rotation. So in this sample input, this is fairly straightforward. Like we can tell that oh, this has gone through 2 rotations. It's moved the A to the other side, and then a B to the other side, and then we get the exact same thing over here. Then we go into our second input, and it's about the same idea, except for this time we're going through a reverse rotation. Is it reverse? Yeah. I yeah, it is reverse. Okay. Anyways, and then the sample 3, we can tell that it's not a reverse because if we actually try and track it, so the way I've found like these are reverse is like basically if you look at these, we could track one point that we know is the same in the string, and we can just like move along in reverse or forward order. So in this case, sample 1, we can go A, B, C, and D, and then where we find that A, we go and we rotate through. So A, B, C, and D. Same for the reverse, we go A, B, C, and D. Except for it won't work here because it's the reverse version, which means that we have to go backwards. So we have to go C, D, B, and A. C, okay. Not in that sense. I meant like A, B, C. It'll go in the reverse order, I mean. So we have to go backwards from the A. So A, B, C, and D over there. In this case, we can't go forwards or backwards in any case, even though the strings have the same number of characters, well, have the same exact characters, but in like a different order. So therefore, it'll be no. So, in order to solve this problem, we have to know what this is. Lexicographical the minimum string rotation. That's a lot of words. I don't want to say it too much, so um, I'll just say minimal string rotation, I guess. But basically, what this means is we're doing exactly what the question asks. We're just trying to identify the minimal rotations of a specific string. So now, if we actually take a look into the algorithms of this case, this is the most basic version of it. And what this basic version does is basically we go through every single rotation, iterate through successive rotations while keeping track of most of the minimal rotations encountered. So that means that for every single rotation that we have, we're going to store it into an array and like keep it there. Then we're just going to compare um, the strings later on, and then if they match, then like we have a fit. Booth's algorithm is a little more interesting because it uses this Kunth-Morris-Pratt string search algorithm. And this is pretty cool. I don't, I'm not 100% sure at how it works, but it basically, from what I've learned, it basically uses the concatenate function, and you basically just keep on adding the strings into a specific order to make searching for the words within like a full string more efficient. From what I've like learned from this. Basically, but like we don't need to go too in depth in that. We just need to know like Booth's algorithm. This is Booth's algorithm right here, and it is also a part of the intended solution. So here, I'll show you guys the intended solution first. So this is Booth's algorithm. We literally just use the exact same function because it does the exact same thing. And all you have to do is just run through it, store every single thing, as we said, every single possible rotation, and compare them. So it's fairly easy. If we want to go into faster run times and better algorithms, I have prepared one for you. So this is uh, one of the more interesting solutions to this problem that I thought I would like share with you guys, because the actual idea around the problem is fairly straightforward. You just find all the rotations, find the reverse rotations, store them all in the arrays, and if you have something, you have something. But this one is pretty cool. I like this solution. Basically, the first thing what we're going to do is create a mod. So this is a prime number, and the reason why we have to have such a big prime number is to avoid false positives. So for example, if I had like a mod of like 7 here, once we're trying to actually, okay, maybe I should give some like context first. What we're doing here is we're basically making a hash map. And what we're going to do with these mods and this x value is create hash keys. So in order to create these hash keys, we want to make sure that we don't actually accidentally uh, put two of the same like hash keys in the same like as equal to each other, because that would mean that like the two are the same string even though they're not. So what we're using here is we're going to use the ACPC values of each of the strings, and we're going to multiply it and like do a whole bunch of math and stuff to create a key, a hash key. And that's exactly what this does. So this is fairly straightforward stuff over here. We just input the number of test cases or passwords. Then we're going to go through and create our own vector. What this vector does is it'll just like keep track of um, the password basically that we're using. So once we go into this, and we also have a hash map over here, or a hash table, I guess, and it's called scene. And we want it to be outside of the while loop so that we can like compare all the rotations afterwards. So once we've gone inside the while loop, this is where we actually import the string. This stuff I'll get into in a little bit, but for now we'll just skip it. So xp is equal to that. I'll skip that too. So now we have a hash table. This hash table is just going to be a temporary one for us to actually find all the iterations, well, I guess all the rotations and reverse rotations of the specific word. So, um, I won't go specifically into this, but I'll tell you about this instead. So hash value will be the value of the polynomial for the current rotation s. In general, if the function of s be the hash value of s, then let s prime be the next rotation. So what this allows us to do is we can actually implement a formula using math to find the key of the next rotation. And what that means is that once we have this formula right here, that means that we can keep on plugging it in to find the possible rotations for every single possibility of the password. And it runs extremely quick at a big O of 1. So that's what we have right here. So this right here is basically just the function of x that I was talking about over here. And what we're going to do is we're going to insert it into our temporary hash table. Then we will also have the same thing over here. Now, this was the thing I told you guys to skip for now. And basically what xp is xp is like x to the power of s. It follows the exact same thing that we've done previously over here. And what this allows us to do, xp times c and c, is basically it rotates where the character is rotated from the end of s to the start of s, given that s is our string. Thus, a one-step rotation of s runs. So, that means that we can basically efficiently create all rotations, and then all we have to do is just move this string and turn it into reverse and then run through the exact same program again. So that's what we do over here. I found this to be like super interesting because like we're just like using math in order to do rotations. Well, I guess like simulate what the hash key value of a rotation would be. And it's super fast. So at this last for loop over here, what we're going to do is we're going to pair our current for loop of hashes to the one in scene. So basically, we're going to try and search for it to see if there's an identical version. This basically means not false. So if it's not false, then it has to be true. So we have to return yes right away. We don't have to do anything. We can just exit the program right away. Else, we insert all of the hashes that we don't have. Well, I guess like all of them. And then we keep on going through our program over and over until either we find one that matches or we turn no. Yeah, it's honestly a super cool algorithm. Both of all three of these I found to be super interesting. This is more, this one right here would be more of the brute force method using, comparing the two, while this is using more of Booth's method algorithm. Yeah, so I highly recommend you guys check this out though. Try and do these problems on your own. Try and figure them out now that you guys know like the ideas around how to solve them. And I think that'll be it for now. Next week, we'll have Dante on. He'll be going over some more of the problems from ACPC 2020, and he'll probably do a better job than I have trying to teach them. Because I didn't teach, well, I didn't create any of these except for straights. That was the only one I created, and straights was like relatively easy. So, hope you guys have a good day. Thanks for coming out here.